Human lungs are evolutionary masterpieces, perfectly optimized for extracting oxygen from the gas-rich environment of our atmosphere. Our respiratory system relies on delicate structures called alveoli, which are built to interact with gases, not liquids. The core problem is chemical concentration. Water contains roughly 30 to 40 times less oxygen per liter than the air we breathe. This means that to meet our metabolic demands, we would have to process a volume of water so vast that our lung tissues simply could not handle the physical stress. In short, we cannot breathe underwater because our bodies are built for a high-density gaseous environment. The physics of water-based gas diffusion is fundamentally incompatible with the anatomy of human lungs. Fish gills utilize a highly efficient mechanism called countercurrent exchange. By flowing blood in the opposite direction to water, they maintain a constant concentration gradient. Compared to parallel flow, countercurrent systems are far superior at extracting oxygen. Parallel systems reach an equilibrium quickly, limiting total uptake. In contrast, human lungs operate on a tide-in, tide-out mechanism. This is physically ill-suited for liquid, as we lack the necessary surface area and flow-through anatomy to process high volumes of water. As we descend beneath the ocean's surface, the ambient pressure increases dramatically. For every 10 meters of depth, the pressure adds another atmosphere, compressing gases and altering how they interact with our physiology. At these depths, even inert gases like nitrogen become toxic. Under high pressure, nitrogen crosses the blood-brain barrier, interfering with neural transmission. This creates a state known as nitrogen narcosis, where judgment is impaired, similar to severe alcohol intoxication. Any viable underwater breathing system must solve two problems simultaneously: efficient oxygen delivery and precise regulation of gas partial pressures. We must filter out nitrogen and manage toxic buildup, essentially acting as a synthetic lung that compensates for the crushing physics of the deep. The future of underwater breathing involves moving away from the limitations of heavy, bulky oxygen tanks. The breakthrough is the nanoporous graphene membrane. This material acts as a molecular filter, allowing oxygen to pass while blocking water and salt. At the atomic level, oxygen atoms are selectively pulled through, mimicking the efficiency of biological gills. These artificial gills represent our most promising path toward independent, long-term underwater respiration, replacing bulky gear with streamlined, high-efficiency filtration. At rest, the human body requires approximately 250 milliliters of oxygen every single minute. This is a constant, non-negotiable metabolic demand. Because water contains much less dissolved oxygen than air, we must process massive volumes of seawater to extract the same amount of gas. This requires high-pressure pumps and constant energy. Current battery technology struggles with the energy density required to power these pumps for long durations. To sustain the required flow, the power source must be large and heavy. This results in the energy paradox. To keep a human breathing underwater, the necessary pump and battery array currently requires a backpack-sized device. We have the science, but we are waiting for the battery revolution. Surprisingly, we have already developed a form of liquid breathing. It involves perfluorocarbon liquids, which are dense, inert substances capable of carrying massive amounts of dissolved oxygen. In medicine, this is used to treat premature infants or patients with severe lung damage, such as ARDS. By filling the lungs with oxygenated liquid, we bypass the physical collapse of delicate air sacs, stabilizing oxygen delivery. While this proves we can survive with liquid in our lungs, it is currently impractical for recreational diving. The high viscosity of the liquid makes the muscular effort required to move it in and out of the lungs far too strenuous for a human to sustain. Humanity's respiratory system is a product of millions of years of evolution. Our ancestors transitioned from water to land, fundamentally locking our biology into air-based respiration. Our lungs are specialized structures optimized for gas-rich air. To extract oxygen from water, we would need gill-like surface areas thousands of times larger than our lungs. Experts agree that full biological modification to create gills is biologically improbable. Our development as land mammals means that mechanical augmentation, not genetic engineering, is our only viable path forward. Looking ahead, underwater exploration will move away from heavy external oxygen tanks. The future lies in soft robotic gill patches. These wearable interfaces will sit comfortably on the skin to extract oxygen from the water. Integrated with neural linked monitoring, these systems will automatically adjust to oxygen levels in real time, keeping the wearer safe at depth. We won't biologically evolve into merpeople, but through technology, we will bridge the gap to survive beneath the surface.